Cool. So last time we started homework 6, which is all about confidence intervals. Which the basic idea is, well, I've got sample mean, sample standard deviation. We're going to use that to build an interval. I actually think I said this backwards last time. Oh, it was sample mean, sample standard deviation. And we're going to build an interval that we think the population mean and standard deviation are in. Or what I forgot to mention, and then it was all what was at the beginning, is you can do the same thing with proportions. So if you got the sample proportion, you try to get the actual proportion. So, the mean, standard deviation, or proportions. All right. Okay. And the thing to remember for doing this, well, for the proportion one, the standard deviation of a proportion is square root of PQ over N. So that means, like when you're doing your interval or whatever, you put in whatever your sample guy is as the mean, put in this guy as your standard deviation, and go from there. If you care about the error, which is the first thing we're going to do in this part, the error all looks like, well, whatever your critical value is of Z, and then times standard deviation. So I'll talk about that just in a second. So that's proportions. When we were doing mean, the standard deviation and the mean, does anybody remember what happens when you take standard deviation for a group instead of just for a single guy? Yeah, you have to divide by square root. So it's whatever the standard deviation for X was over square root of N. And so the same thing whenever we do error here in a second. It'll be whatever your critical value is times that guy. And hopefully, I'm not sure if we'll get this far by the end of the day or not, but for standard deviation, it's kind of the weird one. Let me not talk about it quite yet. So this is the chi-squared distribution. It's the only one that's, we did say last time, it's the only one that's not symmetric in the middle. So like on the mean or whatever, your interval is just, oh, it's the middle plus this guy, the middle minus that guy. But on the standard deviation, it's like the standard deviation is going to be somewhere in the interval, but it's not in the middle of it. It's kind of weird. So, yeah. Cool. So let's hop back to it. Anyway, I want to talk about how to use this error formula thing, I guess, that we're done with. Oh, there we go. So the main practical application of the error thing is, well, sometimes in life you have a particular error that you want, and you want to say, okay, well, I haven't done my study yet. If I want to be within 2 percentage points or something, how big do I need to make the study to get the accuracy I want? So, oh, they went with 2 percentage points. So for this one, they want the error to be 0.02, 95% confidence. And we're going to say that we have some information we think P is about 0.28. So let's go back. This thing. I'm trying to get it to move. It's not doing it. So again, the error is your Z times that guy. So on one hand, I know error is my Z square root PQ over N. The error I want to be 0.02. I'm doing a 95% confidence interval. So how am I going to go about getting this Z here? Any idea? No idea. Okay, so again, confidence means I want the middle slab to be 95%, right? When I do normal inverse or any of those, I always put in area to the left. So if the middle's 95, let me draw a picture instead of just using hand motions. So I want to have 95 in the middle, which means those two sides together are 5%. So this area to the left right here is 2.5%. Right. So to get ZC, I'm going to do normal inverse of 0.025. And Z always, when you just see a Z instead of an X or whatever, it's standard normal. So 0 and 1 for those guys. So, and I guess I need to pull up Excel, don't I? So, normal inverse, 2.5%, 0, 1. So 1.96. 0.02 is 1.96. Square root. It told us in the problem P was 28%, right? .28. So what does that make Q? 72, yeah, 0.72 over N. And from here, it's just algebra, right? So if I get the N by itself, first I'm going to divide by that guy and then square everything. So 0.28 times 0.72 over N is 0.02 over 1.96 squared. And if I want to get N by itself, well, I need to get it on top so I can just flip both sides upside down. So I'm not really sure how many algebra steps to skip, so I guess I'm doing all of them, but that's okay. So if your algebra skills are good and it feels like I'm boring you, I'm sorry. So N is 0.28, 0.72, and then 1.96 over 0.02 squared. Okay. So is everybody happy doing that algebra, or is that? That's all we did. First we divide by the 1.96. Then we just squared both sides to get rid of the square root. And then since N was on the bottom, I just did the reciprocal on both sides to get it on the top. And then to get rid of the denominator, just multiplied by it. Okay. And so we have 0.28 times 0.72 times parentheses 1.96 over 0.2 squared. So we need to talk to at least 1,936.17 people, which I can't talk to a 0.17 person. So you always go out to the next one. So I need to talk to 1,937 people. We're good? All right. Not like that. Okay. So basically the exact same thing. We got 8% for our margin of error, confidence level is 90, and then 20% are first tellers. So again, error is critical Z square root DQ over N. They told us that's 0.08. We'll get that guy in a second. And this guy was 0.20. So the critical guy, oops, I don't know. I'm going to close that because I keep clicking on it. And it's annoying me. It's really weird listening to a movie right behind you whenever you're. Okay. So I want a confidence level of 90, right? So that means if I go back to my picture, I want the middle chunk to be 90. So each side is what? Yeah, each side is 5. So I'm going to do normal inverse with 5% instead of 2.5. So norm inverse, 0.05, 0 and 1. Oops. No, that's not what I want. I have too many points in my point. Okay, there we go. So 1.6. This is the one. Usually you just use 2 decimals in this class. This is the one where they actually do want you to go 1.645. So but okay. So again, you do the same thing as we did last time. So divide, flip it, square it, multiply by those. So you'll wind up with 0.20, 0.80, and 1.645 over 0.08 squared. So since it's the second problem, I can skip all the algebra, right? Over 67, so 68 people. I was kind of hoping there would be one like this, but I'm not seeing one right immediately. So what if we didn't have this prior information that 20%, I mean, does anybody have an idea what we could do if we didn't know those two numbers there? Lane says no. Well, what you can do if you don't know those numbers for proportions anyway is just change it to 50-50. Let's do that right quick just to see how it changes. I mean, the reason is, well, 0.2 times 0.8 is 0.16. 0.50 times 50 is 0.25. If you change it to 50-50, it always makes the product a little bit bigger. So it means, hey, if we don't have any information, we're going to have to talk to a few more people. But we know we can definitely, like if I change this, pretending like we didn't have that extra information. Okay, now I have to talk to 106 people instead of 68. But that'll always work, even if you don't have any idea what you're supposed to do in the real world. Okay, let's go on to about 17. Okay, so now we're going to start talking about the mean. So far we've just been doing proportions, and you use z and the standard deviation is square root dq over d. For the mean, well, the central limit theorem said that if we either know that the original distribution was normal, we can use z. Or if our sample size is at least 30, then we can use z. If neither one of those happens, so here it says the population is very skewed. So this is not normal. Skewed means it's off to one side, right? So we can't use normal because it's very skewed. And also our n is not at least 30. So we have to go with the second route, which is actually, let me make sure. I'm kind of tempted to say we can't use either one if it's very skewed. Yeah, So the short version of the story is if you're less than 30 and you don't have to be normal, but you're reasonably close, then you can use T. If you're less than 30 and you got something really screwed up, you can't actually use either one of them. So, all right, well, let's find one where we actually can use T. Okay. Tell me about this one. If n is 200, sigma is 14, it's very skewed. Can we use either one of them then? What can we do, John? You just guess? So the skewed is bad, right? But that's what the central limit theorem says. If you take big enough groups, the skewed doesn't matter. It will look like a bell curve. Okay. So if n is 200, that's much, much bigger than 30, so I can definitely use the Z. I want to find one where I can actually use T, but okay. How would I find, so if I want 95 in the middle, that means I want 2.5 on each side, right? We already did that. 2.5 on each side was that one right there. So my critical is 1.96. Let's find one more. Okay, here we go. So here n is 15. Sigma is unknown. Population appears to be normally distributed. I'm going to say it's close, so we use T instead of Z. But okay. So let me actually do a little flow chart here. That'll probably be easier. So can I use Z or T? And we're saying this, but I should probably write it down at some point. So question 1 is n at least 30. And then if it's yes, you can use Z. If it's no, next thing you're going to say, well, is distribution normal or at least very close to normal? If the answer is no, you can't do either one. If the answer is yes, the next question is the population standard deviation known? So in real life, the answer will always be no, but at least for purposes of this class, pretend like sometimes it could be yes. So if the answer is yes, then again, we can just use Z. If it's no, this is where we use T. With n minus 1. So T and chi-square have something Z doesn't, which is degrees of freedom. Basically, it's what T looks like. Okay, so if here's Z, then T kind of is just a little bit more spread out. It shouldn't go that high. Oops. If here's Z, then T is just like that or something. This would be really spread out or something. So basically, this is low degree of freedom. As the degree of freedoms get higher and higher, it starts looking more like the regular bell curve, if you like the picture. But, all right. So, and again, the two functions, the one you're usually going to be using is T inverse. You could use T dist if you absolutely needed to. Okay. All right, so right now, the population's unknown. So does that mean we use Z or T? Yeah, we use T. And so if N is 15, well, one less than that, we use 14 degrees of freedom. So, and we're doing 90% confidence. So middle's 90, that means the left-hand side is 5%. So we're going to go, so T inverse. The probability is 5%. And then it doesn't even ask for the mean and standard deviation. It knows we want 0 and 1, so we don't have to do that. It does ask us, though, I don't know if you can see it there, but it asks for degrees of freedom, so 14 degrees of freedom is 1.761. Easy enough? All right, let's do another one. And it's 25. This time the sigma is actually known, and it's normally distributed. So can we do either one? So first thing, N is less than 30. Is that okay? No, that's bad. So we go on to the next thing. Is it normally distributed? Yes. So we can use either Z or T since it's normally distributed. That when it says sigma is 28, sigma stands for population or for sample. So just recap from the beginning. So again, the difference between we have different symbols for them. So for population, we go mu and sigma. For sample, we go X bar and S. And standard deviation. So when they say sigma is that means, hey, we do know the population. So if we know the population, does that mean we have to still use T, or can we use Z? Yeah, we can use Z. So it's going to be just like the ones before, where just go normal inverse. We're doing 99% confidence. So what's the area to the left? So 99 in the middle. That means the two sides together are 1, which means one side is 0.005 and 0, 1. So 2.7, there we go, 575. All right, let's actually build some confidence intervals. Let's go to maybe 24, see what happens. And a sample of 7 cars. Each car was tested for nitrogen oxide emissions. Following were obtained. That assuming that's representative of the cars in use. Construct a 98% confidence interval for the mean. The EPA requires to be less than 0.165. Can we safely conclude this requirement is being met? Okay, so and next cell. All right, so first thing we're going to do is find the mean and standard deviation both. There's that. So that's our mean. That's our standard deviation. All right. So are we going to be using Z or T? Do they tell us anything? I mean, presumably it's normally distributed or we couldn't do anything, right? So we're going to just kind of go with that. Do we know anything about the population standard deviation? Do they tell us anything about that? No. In real life, you almost never know that. So That means we're going to have to use T instead of Z. We want 98% confidence interval. So what's the area to one side? 1. So we're going to go T inverse, 0.01. And degrees of freedom, well, we have 7 in our sample. Degrees of freedom is always 1 less. So 6. So that's our critical value. What do we do now? We haven't actually done it yet. We just talked about it. So we said for mean, the error is your critical value, which is either Z or T. And then the standard deviation is X bar over square root of N, right? So for this one, we just got T was what? 3.143. That's surprisingly close to pi. That's a total coincidence. But so our sample standard deviation, oh wait. I knew something looked funny when I wrote that down. Sorry. This is standard deviation. Not bad. Our sample standard deviation is the 0.0035 over square root of 7. So that's our error. And so our confidence interval is going to look like, well, our sample mean, which was, so mean minus the error is less than mu, is less than mean plus the error. Okay. Our sample mean was the 1571 guy. 1571 minus that to 0.1571 plus that, right? Okay, so we just need to punch in and see what that is. So the error is, well, it's that critical value. Let me make it positive. Times the standard deviation over the square root of N. Right. And then so our interval so on the bottom, we could have the mean minus the error. On the top, we have the mean plus the error. So we're reasonably confident that the real mean is somewhere between 0.117 and 0.197. Clear as mud. It's actually really easy once you do a few of them. So could you conclude that this batch of cars was safe according to the EPA? EPA says they want 0.165.
Yeah.
Well, what we really want is the mean is less than 0.165, right? Which it might be. I mean, the mean might be down on the 0.117 end, which would be fine. But we can't say for sure that the mean isn't up there on the 0.197 end. So we don't, the data we have doesn't say that, yes, the mean is definitely below 1 point or 0.165. So, yeah, it's possible the requirement's being met, but it's also very possible that the mean is not less than that. So, all right, let's do another one like that. So 12 video games showing substance abuse were observed in duration time listed below. Design Justifies the assumption that the sample can be treated as a simple random sample. Use the data to construct a 99% confidence interval for mu, the duration of gameplay.